Okay, so um, to the three of you who are here so far, welcome. Figured I would log on a little early and then make my grand entrance. The way this is going to work is that I am going to be here for an hour if there's enough interest, and I am going to answer whatever questions you have about the first unit in chemistry. If we need to do any calculations, got my calculator right here. I did download that new Mario Kart game this morning, and that was a mistake. But I'm gonna stay off of it while I'm talking to you guys. I have a clipboard if I need to show you anything on paper. I will need to grab a pen, but I see one right there on my desk. And otherwise, any questions that you have, go ahead and hit me up in the chat window on the right hand side of your screen. And if you have any questions which you'd rather not put there, feel free. You can also email me. I've got my email open and I'll check it periodically just to make sure that we're on track. So let's, before we get started, because I don't see any questions just yet, I want to clue you in a little bit about what this test is going to look like. So I'm going to open it up right here. As much as you might hope this will happen, I'm not going to tell you any answer keys here. So we have, it will be an 80-point test. Not that that matters because tests are their own category on Power School. But there will be, oh, and Mr. Hands has done a lot of really nice formatting, so it looks very nice now. There will be 15 multiple choice questions. There will be, I believe, 8 open response questions, and one of them is going to be a practical question where you are going to do an experiment and write down your observations and then answer some questions about what you're seeing. You may think about what we've done in this unit. We've done a brief lab on density. We've done a lab on physical and chemical changes. So probably it'll come from one of those areas. So that is what the CP test will look like at the very least. I can't speak to anything on the honors test, but I imagine the content at least will be pretty similar. I don't have any role in making up that test, but I would imagine the content that we'll talk about tonight, as well as the content on your test, will be a little similar. Will be very similar, maybe a little more in depth. If you'll excuse me, I'm going to take a sip of my tea. Trying the winter wake up tea from Trader Joe's. I'm trying to be a tea guy, big coffee guy for many years. Trying to embrace tea at night, especially, so I'm not up all night. We'll see how it goes. The winter wake up tea. Good choice. Highly recommend it. Get yourself to Trader Joe's and get some if you're into tea. Okay, so questions. Lay them on me. If I don't get any questions, I'm happy to go through things in general. You may have noticed because probably you got here by going to my YouTube channel. And if you look below this window, I think that's how the live stream works. There's a window up top, and then you can see all my videos below. There should be a listing of all the other videos that I uploaded. I've taken time to upload kind of all the kind of general videos that might apply to this particular unit. And so there's some dimensional analysis examples up there. There's a couple videos about Sig Figs, both general rules for Sig Figs as well as what we do when we add and subtract, as well as what we do when we multiply and divide. Those rules for rounding are going to be really important when we do calculations. The nice thing about rounding when you get into dimensional analysis, for example, is that most of the conversion factors that you use in dimensional analysis, when you set up your grid, and if you're in my class, you know I'm insisting on that grid. You're going to have to show the work my way. That's sort of the one thing I'm not going to budge on. Um, those those conversion factors, sorry, lost my train of thought, um, are considered to be sort of numerical definitions, and so they're considered to have infinite sig figs. So the beauty of that is that when you're doing a calculation with dimensional analysis, the only measurement you have to worry about is the very first one. So if I ask you to tell me the number of seconds in 365 days, then you would know to round to three sig figs, because that would be because there are three sig figs in 365. So the old musical theater song 525,600 minutes, that actually wouldn't be correct, because you would have to round a bit further to say 526,000. A good tip when you're rounding is to put something into scientific notation first. So I'm probably going to make up a problem here, so it might take me a minute to make sure that the numbers work out right. Let's say, let me go ahead and clear out my calculator here. Excuse my reach. So I'm going to make up a number here. Let's say 34.7 times 0.0042 divided by 173,000. So, so if I do this calculation right here, 34.7 times 0.0042 times 173,000. And somebody please let me know if it's backwards to you. It's backwards to me, but I'm pretty sure YouTube flips it. So if I do this math, I'm going to go ahead and get 0.0042 divided by 173,000. I know this makes for fascinating viewing, listening to me talking about numbers. I get 0.00000084. Now, I was really hoping that I would come up with an example that didn't work out perfectly. You can see here that based on what we see, the rule for multiplication and division is that we have to take the number with the fewest sig figs among the ones that we're measuring, among the ones that we're doing the math for, and our answer needs to match that number of sig figs. So, in this case, that number of sig figs would in fact be 2. And that's literally what I got in my calculator, 0.00000084. Now, my calculator just went a little insane. My apologies. So if I needed to round differently, then I could put this in scientific notation, and I could just round after the fact. So if I were to do that, now this right here is a very, very small number. And the rule that I tend to follow is that if a number is less than 1, if it's a decimal, for example, then you're going to always use a negative exponent. If it was a very big number, a number that was greater than 1, it didn't have to be very big, but if it's a big number, then you would use a positive exponent. So we know that the number of the exponent is going to represent the number of places we have to move the decimal point. And in this case, that is 1, 2, 3, 4, 5, 6, 7. You can see there that I've moved the decimal point 7 places to get to a base number between 1 and 10. Remember, that's an important part of scientific notation. So we have 8.4 as our base number. And then because we move that decimal point 7 places, because we have a very small number that is a decimal that is less than 1, our final answer for that, if we were asked to express it in scientific notation, would in fact be 8.4 times 10 to the negative seventh. So I see that an email's come in. Let me just make sure that that's not a question. It is not. This is other very exciting news, which I'll talk about later. But now, so we've talked a little bit about Sig Figs. We've talked a little bit about scientific notation. I'd love to take a question from the crowd. So if you've got a question, go ahead and type something in the chat window right there. Also, feel free to drop me an email and we will get some more good stuff done. So lay it on me. Who's got the first question? Okay, so Brooke has a question that may not necessarily come up in this level of depth on the test, but she asks, "Is milk a colloid?" So one type of technically heterogeneous mixture that we talked about briefly, but may not have gotten into in detail. I know I did in my classes. Were colloids and suspensions. So the difference between the two lies in the size of the particles that are sort of suspended, for lack of a better word, in the liquid. So colloids and suspensions are both heterogeneous mixtures in which you have a liquid phase and a solid phase. So in a colloid, those particles are too small to really be detected. They're essentially invisible. So milk is actually an example of a colloid, at least when that milk has fat. Skim milk, which doesn't have fat, would not be a colloid. A suspension, on the other hand, would be something like why can't I think of anything? Would be like the oily part of Italian salad dressing, for example. So like if you had oil, like the dipping oil that you get at the Olive Garden, that would be a great example. You put a bunch of spices in with that oil, and those particles, those very large visible particles, are suspended in there. So that would be an example of suspension. Technically speaking, both of those would be heterogeneous mixtures. As far as I remember, we don't get quite that nitpicky on the test. However, it is something that kind of comes up if you're getting really nitpicky about the types of mixtures. So while we're at it, since Brooke got us talking about mixtures, let's talk briefly about the classification of matter. If you want to go in another direction, feel free to lay a question on there. But we break up matter into two broad categories. We can talk about pure substances and we can talk about mixtures. Now, the general rule is that a pure substance is made up of only made up of only well. So there are two types of pure substances. Let me back up a little bit. There's an element which is made up of only one type of atom, and that is considered sort of the smallest form of matter that still retains the properties of that matter. So, aluminum would be an example of an element. Oxygen would be an example of an element. Some of those elements do take the form of molecules where more than one atom is combined. However, as long as it's only one type of atom, one atom of an element, for example, then that would still be considered an element. Basically, if you can find the symbol for something on the periodic table and it's just one symbol, then you've got an element on your hands. Now, if you put one or if you put two or more of those elements together, then you have a compound. And in a compound, those elements are chemically combined. That is, they form a bond, an ionic bond, a covalent bond, or something in between. We'll talk much more about those in future units. So, the general rule is if you can come up with a formula for a substance, and the example I always give is sodium chloride salt. If you can come up with a formula for a substance, and it contains more than one atom, it's probably going to be a compound. So NaCl would be an example. That is sodium chloride salt. H2O would be another example. CO2, carbon dioxide. I could go all day. I could get really obscure if you wanted me to, but like glucose, to take an example from your biology class, would be another example of a compound. More than one type of atom, but those atoms are chemically combined. That is, there is a bond between them. So then we have mixtures. This is very good tea. So the mixtures fall into two categories: homogeneous and heterogeneous. And when we talk about mixtures, a word that you often hear is the word phase. And a phase is an area of a mixture, an area of any substance really, with a uniform composition. That is, it's the same throughout. Now, in a homogeneous mixture, there's only one phase. So Kool-Aid is the example we usually give. If you make Kool-Aid correctly, and people have their preferences for Kool-Aid and all that stuff, but if you make Kool-Aid correctly according to the instructions, then everything dissolves. And when you look at Kool-Aid, it's just uniformly red or blue or whatever, throughout. There's no areas where it looks different, where it's a different color, where there's other stuff. And that would be an example of a homogeneous mixture. Homo meaning the same. A heterogeneous mixture would be, for example, I mean, cereal. One of our favorite cereals here in the Bryan household is the Kashi family of cereals. We convince ourselves that we're eating healthy, but we're just eating breakfast cereal. It's healthy cereal, I guess. But anyway, if you look at breakfast cereal, the kind we're really digging right now has like a little bit of maple flavor, and it's got like these little nut clusters, and it's got flakes, and especially when you add milk, you've got all these different phases, all these different areas of different composition. So that's a great example of a heterogeneous mixture. Um, Generally speaking, when we ask you to sort of identify what's what, we're going to try to find fairly common examples that you would know. In the past, we've run into issues where like we know very well what these things are, but like your typical high school student doesn't. So we try to stay in touch with these things. So let's see. So it appears that if you're on here, oh hey, Lauren Brooks just figured it out. She just emailed me. So it looks like there's lots of my soccer players on here. Hey, girls, I just saw you. So first things first, Peyton's question was, what is the rule for adding and subtracting sig figs? If you need a little refresher, I would refer you to the video that I just uploaded a few hours ago. Actually, within the hour, I was watching Bob's Burgers while uploading a video, and that actually summarizes all the rules. So if you need a refresher after this, feel free to hit it up. So I think I went over the rule for multiplying and dividing sig figs pretty well. The rule is the measurement with the fewest sig figs is the one that you have to round to in your answer. So the rule is all about sig figs. So let me give you an example, and I'm going to set it up in a way that's really going to show it clearly. I'm going to set it up in that old school way where you learn to add. So I'm going to come up with a number, let's see, 2.9 plus 7.43 minus 4.727. So here are my three numbers, just like that. Now, the rule for adding and subtracting is that your answer should match the fewest decimal places of all the measurements that you have. So, for example, if you had a whole number in there, if you were adding a bunch of measurements and one of them happened to be a whole number, then you would round to the nearest whole number. You would leave all the decimal places off. And I know that's kind of weird. I know your mind kind of wants to just put what's on the calculator there, but these rules for rounding are very important because it allows us to, we can only be as precise as the least precise measurement that we have. And while the rules for adding and subtracting are different from those for multiplying and dividing, it's really important that we not try to get away with more precision than we actually have. That's why Sig Figs exist, to make sure we can measure things as precisely as possible, but no more. So I'm just going to do the math real quick here. 2.9 plus 7.43 minus 4. I'm bad at calculators, apparently. Let me try this again. 4.727. So the answer that I get is 5.603. Now, the measurements that I had, I'll just put this up right next to the screen. And Mia, surely you have something better to do. I mean, I'm glad you're here. But so of those three measurements, we need to look at the one with the fewest decimal places. So obviously, that one is 2.9. That was a shout out to you, Cassie, if you didn't notice. And that means that we have to round this to one decimal place. That means that our final answer would have to be 5.6, just like that. So hopefully that was a good review. Peyton, let me know if there's anything else you need me to clarify. And otherwise, I'm going to go ahead and go on to Lauren's question. This is becoming just an extended soccer practice, except we're talking about chemistry. Not complaining. So I think the easiest way, and shout out to Ms. Thorne for actually cluing me into this. I've been teaching the concept of percent error for years, and it's always been really clumsy the way I've done it. And I think I've got a simple, easy to understand way to figure it out. So percent error is all about, so sig figs are all about precision. It's all about how much you can know about a measurement. The more sig figs you have, the more you actually know for certain about that measurement. That's why all those placeholders, the ones at the end of a number without a decimal point, or the ones between the decimal point and the rest of the numbers in a decimal, aren't significant, because while they're important for you to know how big a number is, how large a measurement is, or small, they don't allow you to measure with any more precision. They don't allow you to know really any more about how good the measurement is, I guess. Percent error, on the other hand, is all about accuracy, all about how close you get to what you should get. The example that we've talked about, if you'll allow me a sip of my tea. The example that we've talked about in class, and I think that the other chemistry classes did it a little better than mine because I missed an opportunity to do it like way at the beginning of the year, is the density calculations that we've been doing. So let's say, for example, that you know that the density of aluminum is, so the known density of aluminum is 2.70 grams per milliliter. That's just the one I could remember off the top of my head. Now, you, a very good but not perfect chemistry student, you get a measured density for aluminum of 2.55 grams per milliliter. So, what we're going to do here when we calculate percent error is we need to consider two measurements. We need to consider the one that you get, which we would consider an approximate value because it is by definition not exact because you're a human and you're fallible. You have flaws. Sorry, guys. And the exact value, which is the one that is generally accepted by the scientific community. You may hear this referred to as the accepted value or the theoretical value. There are lots of ways to say this. I really like this because I think it's easy to understand. The exact one is the one you should get, and the approximate one is the one that you got because you're not perfect, and that's okay. So, if we set this up, we know the approximate value, and I'm going to put this up in a minute to show you. What I should have done is brought a whiteboard home. That would have been a much better idea. I'm just going to go through a lot of paper. So your approximate value, the one that you got, was 2.55. So that's our first term. Then our exact value would be 2.7. That's what the textbook would say. That's what scientists generally accept as the density of aluminum. And then we would divide again by that exact value. And then to make it a percentage, we would multiply by 100. So our work would look like that. 2.55 minus 2.70 divided by 2.70 times 100. Now, very important order of operations note here. If you put all those numbers consecutively into your calculator, you will mess this up because your calculator follows order of operations. You remember PEMDAS. It's going to do multiplication and division first. So it's going to divide 2.7 by 2.7. You're going to be subtracting 2.55 minus 1, and that's going to be a much bigger number than you want. Don't do that. Don't be that guy. So you're going to do the top first. So if I do this out, our next step is going to be negative 0.15 over 2.70 times 100. I swear there's a decimal point in there, although I did not put a decimal point. I'm surprised nobody caught me. And then we're going to get a value of 5.55 repeating percent. Now, I would say you should round this to the nearest tenth. So let's go 5.6 on that one. Now, the answer that you would actually get is negative 5.6%. Why is it negative? It's negative because the value that you got, your approximate value, is less than the accepted or the exact value. That's not any cause for alarm, but it is sort of numerically important because it tells you whether you're too low or too high. So if somebody else came off the street and they saw that you had a negative whatever percent error, they would know, okay, this person got a lower value than they should have gotten. So hopefully that helps clear that up. Lauren, give me a holler if you need something else with that. I don't know if that's something that you went through. I just happened to see it on a worksheet that Ms. Thorne was doing, so I totally just stole it from her. I think that's what a lot of teaching ends up being. You see good ideas and you take them for yourself. So, Cassie and Peyton. Let's talk about, and tea isn't great when it's lukewarm, but still tasty. Physical and chemical changes. So, in a physical change, excuse my fidgeting here. In a physical change, you're changing something about the substance, but you're not changing its chemical composition. So, most of the changes that you would consider to be physical changes would be phase changes, changes in phase. So, from liquid to gas, from gas to liquid, from solid to liquid, etc. We're going to go over those phase transitions in detail in the next unit. We're actually going to do a unit on heat right after this. But boiling water would be an example. Ripping paper, and I think that's the example that we used in class. I told you to perform a physical change on paper, and you tore it in half. That was pretty good instinct on your part because that, in fact, changed something about the paper, its relative size, but it didn't change the chemical composition of the paper. So those most of the examples of physical changes that you'll come across are phase changes. You got to be careful sometimes though, because if we're talking like in a biological context, like one of my favorite things to do to trick people is to bring up like a broken leg repairs itself. That's one that shows up every so often. A broken leg repairing itself actually involves a whole lot of chemical reactions. I'm the anatomy teacher, and we're in our biochem unit right now, so that's what we're talking about all the time. So much of what we talk about in anatomy from a physiological standpoint, the way things work, is that those chemical reactions that make things happen. So you got to be a little careful when you're thinking about those things because, like, grass growing is involves a ton of chemical reactions. Those cells have to grow and divide and make copies of themselves, and all of that involves chemical changes. Chemical changes involve a change in the composition of the chemical composition of the substance. So the atoms actually get rearranged. In a physical change, on the other hand, the atoms might spread out, they might become more compressed, but fundamentally, those atoms or molecules are still the same substance when you're done. In a chemical change, all bets are off. They get rearranged, they find new partners, they form new bonds, they break bonds that they had before, and you have a new substance in the end. So, burning is a go to example. The color changes that are occurring in the leaves right now, you're seeing leaves everywhere. It's beautiful. Some of you might have gone and seen the foliage this weekend. All of those are examples of chemical changes that are occurring in nature right now. And so the signs of a chemical change that you're going to look for are like a color change is often the sign of a chemical change, not always, but often. You may remember in the lab when we made the canary poo, um, we combined a white powder with a clear solution, and we ended up with a yellow precipitate. A precipitate is just a solid that you get in a chemical reaction. So a color change is often a sign of a chemical change. Often you will see a change in temperature as heat is released or absorbed. The like hot packs that you like the hand warmers that you might use in the winter. We use hand and foot warmers quite a bit when we're hiking in the winter. Winter hiking is awesome. You should all go. But it's cold. So we need to make sure that our hands and feet stay warm so we don't get hypothermia, so we don't get frostbite. Had a big hypothermia scare a couple years ago on top of a mountain, which wasn't great. But we had hand warmers. And so there was a chemical reaction that happened in there that released heat and kept me from losing my fingers. That was pretty nice. So that's one sign. One that we saw quite a bit in the reactions that we did this unit was the production of a gas. Anytime you see bubbling or fizzing, that's usually a sign that a gas is being produced. And so those three, as well as the production of a new substance in general, that often is accompanied by a color change or the production of a gas. Great example is burning. When you burn a piece of paper, for example, what you end up with is not paper. It's ash. It's a very different substance. Rusting metal is another example. When you're done, you end up with something that is a different color. It's very brittle. It has very different properties from the substance that it came from. So, hopefully, that's a good summary of examples of physical and chemical changes and the science of chemical changes. I gave you extra there. So, Emma Fitzpatrick is asking us to go over unit conversions, please. So, there are kind of two aspects of this. There's the dimensional analysis piece, and I think it might be worth going through a dimensional analysis problem. And I'll probably stick to something fairly common. Actually, here's what we'll do. We can actually take care of both with one problem. Give me a minute. I'm actually going to go. Actually, just give me a minute to stare down at my paper, play some music in the background, do what you got to do to make this entertaining, and then I'll be right back. Okay, so I've come up with a problem, a very personal problem. And so let's see. I'm going to cheat and look up one conversion factor here. I would give you any conversion factors that you need. Okay, so here's the problem. I weigh 160.2 pounds. How many milligrams do I weigh? So this is a problem with like zero practical application, but I think it covers a lot of the bases you're talking about. So let's go through it. So when we do dimensional analysis, first of all, I'll go ahead and throw that in too. There's always a number in the question where we're going to want to start. And so read the question very carefully, look for some numbers. Sometimes it might just say in one something, or sometimes the number might be written out. So look for a number. In this case, the number is pretty obvious. We're going to start with 160.2 pounds. So I'll go ahead and set this up, and then we can take it from there. So there is our start. You see that I've put 160.2 pounds on the upper left-hand side, and I've set up a grid for our next step. Now over here, I've gone ahead and written kind of the general rule of thumb for any conversion factor you're going to use. Two rules that you got to follow. You've got to cancel the unit before, and unless it's the last step, in which case you're just going to solve the problem, and the two things you use in each conversion factor have to be equal to one another. So it would be very useful, especially if you're the kind who struggles with this sort of stuff, who doesn't have a great instinctive grasp of math, to write down all your conversion factors first, just like this, like one thing is equal to another. So, if I'm trying to convert based on the information that I have, I'm probably going to want to convert from pounds to some other unit. And it looks like the best conversion factor to use is this one right here. 1 pound equals 16 ounces. Now, I'm going to put pounds down on the bottom because I want pounds to cancel. The rules here are the same as they are for fractions, where if you had something on the top and the bottom, you would cancel it out. Except now we're trying to cancel out units, and we're carrying whatever numbers are attached to those units with us to do our math. So if I set up this next step, 1 pound goes on the bottom, and then 16 ounces goes on top. So if I were to stop right there, if the question was how many ounces are in 160.2 pounds, I would simply take 160.2 multiply by 16. I'm going to leave out the 1 because we can essentially cancel that out. And now I know that I can cancel out those first 2 units. Now, at every step, I want to check to make sure that I haven't already finished, because sometimes you kind of overshoot. You do too many steps, and then you've missed the answer that you already got. In this case, we weren't asked about ounces. We were asked about milligrams, so we're going to keep going. So the next conversion factor that I have, it looks like I can convert ounces to grams. So I'm going to use this, and I'm going to be able to cancel out ounces by putting that on the bottom. And of course, on top, because they're equal, I'm going to put the other part of that conversion factor, namely 28.3 grams. So again, I want to check. I want to figure out if I'm done. Now, I personally, and I can't speak for my colleagues, I would be okay if you stopped here, solved for grams, and then converted to milligrams. So let's just for the sake of argument, do that right now. I'm going to go ahead and calculate this calculation. And I'll try to keep this up on the screen while I do it. I really need like an assistant here just to hold this up. Or I could come up with some sort of rack to do that. So my math is going to be 160.2 times 16 times 28.3. And I'm going to get this 72,538.56. So in this case, I got to worry about rounding. Now we've multiplied and divided. So, and dimensional analysis is all multiplication and division. So it's going to be really easy to figure out sig figs because all you got to do is look at this first number right here. So that number has 4 sig figs. Our answer's got to have 4 sig figs. So if I write down 72,538.56, I know that I'm going to have to round after this 3. And I'm either going to round up or I'm going to round down. So I would, in this case, because I need to make sure I keep this number the same, so I can't just get rid of these numbers. They exist. They matter. I need to make sure that this number, when I round it, is about what it was before. So this number's got to be about 72,000. So, but one thing you may have noticed is that I haven't finished yet because the answer asks me how many milligrams I weigh. And that number is going to be a lot bigger than this. Now we know that if we look at our conversion chart, which I'm writing down here, sorry for the delay. So you're going to be given something like this on the test. You need to be able to know how to navigate it. So if I'm going to the right on the chart, yes, you will. I just said that. And so over here, if I'm going from the base unit, which is where I am right now, because this value was in grams, because that's the unit I had left over. If I'm going from the base unit to milligrams, then I would make sure that I would move, sorry. Then if I'm moving from the base unit to milligrams, I would move my decimal point to the right. These are smaller units, units that are smaller than the base unit. As such, we would have more of them in a given amount of something. So, like in this mass, we would have more milligrams than grams. Milligrams are a smaller amount. A typical dose of Aleve, for example, I take Aleve every morning because I'm old and I ache, um, is 200 milligrams. If I were to convert that to grams, it would be zero point 0.2 grams. It's a little easier to understand in milligrams because it's not a weird decimal. Um, so if we do that math, we would see that we would move that decimal point 3 places. Put that right there, and I would end up with 72,000. Whoops. 72538,560. So 72,538,560 milligrams. That makes me feel fat. I'm gonna go cry now. But again, we got to make sure we round. So here's my advice: to make sure you don't round badly. Robert, you're gonna go bye-byes. It's exactly the kind of crap I was talking about. So, if you put this in scientific notation, then you won't have any issues. So, 1, 2, 3, 4, 5, 6, 7 places is how many I need to move to get to that base number that's between 1 and 10, 7.2. So I'm going to go ahead and say 7.254 times 10 to the 7th milligrams is going to be the best answer. That way, you're not going to be tempted to just get rid of all these zeros. That's real dangerous because a lot of people would answer this 7,254 and they'd be real wrong because that number is way bigger than that. So you got to be careful about that. Lauren, I don't know if the honors classes are going to get that, but my advice would be to memorize that very simple chart because it is very simple and to write that at the top of your test. There's nothing to stop you from that. I've actually had kids do that quite a bit. Like before they even see that there's a conversion chart in there, they just write it as soon as they get the test. So that would be a bad idea. So I actually just saw a revised version of the test though, and the CP test does have that metric conversion chart. So you're good. We got about 10 minutes left. I got 8:48. Robert's going to be back in a minute. I don't know what that dude's up to, but if he's one of your friends, shame on you for letting him know the link. If you have any more questions, I am all ears. I'll just double check that there wasn't anything here. Looks like Emma was able to get through after all for her unit conversion question. If there was any follow-up on that, feel free to hit me up. I think we've gone over a lot of the really big things. There's a lot of little things in this unit. I don't always love it, but I think it's really good to build a foundation for what's coming. You'll notice that this stuff comes back again and again and again throughout the year. Pretty much everything we've done in this unit. So if you got any more questions, I'm all ears. Or if we're good, we can wrap this up early and we can all go on with our night and see if that black hole's disappeared from Fortnite. I'm actually way too interested in that, by the way. It's sort of fascinating. They do really good work. All right. So, give you about another minute, and we will see if we have any more questions. Otherwise, I hope this has been productive. I hope that we can get a lot out of this, and tell your friends that it's up here. Don't tell Robert, but anybody else who might need to brush up on some of this basic stuff. Hopefully, I gave some good examples of unit conversions, of Sig Figs, of the classification of matter, of physical and chemical changes. It's a little hard to hear it talked out, but I know my classes, you also have notes. I sent you notes on all of this stuff, and so we should pretty much have everything we need. You also have answer keys to all the homework, so make sure you check those out. There are some good examples there. And frankly, there are only so many things that we can ask you. So if you've studied up on some of this stuff and you've seen some good examples, then I think you'll be just fine. Brooke, I'm glad you liked it. Glad you got a lot out of it. Tell your friends. And other than that, I think we've probably given everybody enough time. So let's call it a night. Any last minute questions before I sign off? All right. So thanks for coming, y'all. Tell your friends, like and subscribe if you're so inclined. Until next time, good luck, study hard, get some sleep, and we'll see you tomorrow.